We're going to start streaming soon. Just 1 second. Gotta check. Make sure all the infrastructure is perfect. Alrighty. Good morning, good afternoon, good evening, and today we are looking at another paper. The paper week continues. We've been going heavy on papers this week. Next week I hope to do some more coding. I have some libraries that I've been saving, so look forward to that next week. A little bit more coding heavy. This week a little bit more reading and paper heavy. So today we have a paper called TorchScale, Transformers at Scale. This is also a relatively fresh paper, and it's coming out of Microsoft, kind of a big team there. So when you see these big tech companies and then you see a ton of names on the paper, that's how you know that there's a lot of work that was done for this paper. There is a GitHub for this paper, TorchScale, Microsoft. Here you go. It's basically a Python library that allows you to scale transformers more easily. And really what I'm hoping for reading this paper is to kind of see a couple tricks that they have for scaling, right? These kind of libraries, usually the paper is kind of like a bag of tricks kind of paper where they show you all these different things that they did to be able to scale it. So excited to see what happens there, and maybe we can try out the code next week. 1 second. All right. So large transformers have achieved state-of-the-art performance across many tasks. Most open source libraries on scaling transformers focus on improving training or inference with better parallelization. In this work, we present TorchScale, an open source toolkit that allows researchers blah, blah, blah. TorchScale has the implementation of several modeling techniques, which can greatly improve modeling generality and capability. Okay, so improving generality and capability, as well as training stability and efficiency. Experimental results on language modeling and neural machine translation demonstrate that TorchScale can successfully scale transformers to different sizes without tears. Or tears. I think that's a tongue-in-cheek joke there. I don't think they actually mean there's a technical definition to tears. I think that literally is just a joke. All right, so recently there is a trend that the transformers have become the de facto backbone. I would agree with that. I think, for example, in the paper yesterday, we saw that instead of a ConvNet for encoding images into a latent space, they use the VIT, the vision transformers. So I would say once you start seeing papers that are no longer using the ConvNet backbones, the age of the transformers has begun. I would actually say it began maybe a couple years ago. Convergence is much faster. More emergent abilities are observed in the larger models too. Okay, so here they reference some other systems that have tried to kind of scale transformers, and there's different ways of scaling, and one of them, for example, is model parallelism, pipeline parallelism, expert parallelism, and optimizer parallelism. I'm sure they'll define these later, but it's basically you're choosing what part of your compute to spread out onto multiple machines or multiple GPUs, right? So in model parallelism, you might take your model, which itself is very big, and then spread it out over several machines so you can fit it on multiple GPUs. Expert parallelism, for example, is when you have a mixture of experts, maybe the final answer that you want is actually the result of several different transformer models. So you can basically run each of those separate transformer models on their own hardware and then combine them at the end to get the final answer. There's a lot of different tricky ways to do parallelism with, like, for example, the batch, and even within the model itself, you can have different parts and batches of the model. But yeah, we'll likely define those further down in the paper. So this is really what they want, right? Generability, stability, and efficiency. Those are the three goals of scaling here. Multiple transformer variants. So here's a couple transformers that they reference here: post-LN, pre-LN, Magneto. Magneto is a foundation transformer for general purpose modeling, which serves as a go-to architecture. Okay, so apparently Magneto is a transformer that is used for language modeling, machine translation, and vision pre-training, speech recognition, and multimodal pre-training. Magneto is simple and efficient. LN here stands for layer norm. So normalization on an individual layer level. So, right, if you think of a fully connected neural network, it's not exactly what it is here, but I think this is a good way to think about it. You have a fully connected neural network. Each of those layers, right, there's going to be a bunch of these numbers, and some of those numbers are going to be big and some of them are going to be small. And what you can do is you can normalize all of them, right? So you can normalize all of them with respect to every other number in that layer. And what that'll do is it'll kind of prevent individual neurons in that layer from becoming kind of too powerful, right? If you don't have this normalization, some of these neurons will fire very high and they will always have a very high number there. And then some of the neurons will kind of become dead neurons, where the numbers that they have are very, very small, and they always are small, and because they're always small, the gradients that they get are small, and then kind of just become dead over time. So layer normalization allows you to kind of take the highest number neurons there and make them smaller, and then take the lowest number neurons and make them larger. Damn, I wish I could explain things better, but the terminology is just not great. Okay, so TorchScale has encoders, decoders, encoder decoders. Okay. So this is interesting. This means you could use TorchScale to train encoder with a self-supervised or unsupervised training objective. So let's say you have a bunch of unlabeled training data for some weird niche application. You could use this library to, since they have an encoder decoder, figure out what an embedding space for that is. Okay, figure 1, scaling up experiments, scaling depth and scaling width. So width and depth are two different size dimensions for the a neural network, right? You can think of depth as roughly kind of the number of layers, like how many layers are there successively. So if you have a little fully connected, let me actually get a picture. Fully connected neural net. So in something like this, the depth in here would be 1, 2, 3, 4, 5. It would be 5 because this is 5 layers deep. But the width is going to be the kind of this here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 neurons wide. So you can scale things deeper or wider. There's different trade-offs, and it's still not actually fully understood, to be honest. It's still kind of the black box of just function approximation with neural networks in general, where in some problems, depth gives you more capacity, in others, width gives you more capacity. A lot of times, the width is more determined by the dimensionality of your input, and the depth is determined by the kind of compute that you have. So usually the width and the depth, those get chosen for you, right? You make the width the size of your input, and then you make the depth however much memory you have in your GPU, and you kind of try to make it as big as possible. But overall, they're just kind of showing you here 12 layers, 24 layers, 48 layers, 96 layers, and I don't know what PPL is, but some kind of loss, right? And it shows you how the bigger models get lower losses. And then here you have experts. So maybe width, they don't necessarily mean the number of neurons in an individual layer. What they mean is in a mixture of experts, there's more or less experts, right? So it's like how many of these individual models are kind of stacked along the width dimension here. So if you have 16 experts all the way to 256 experts. They should have said what PPL means. I feel like in this figure description here, they should have told you what PPL means. As the model grows, one problem is that transformers are more unstable in optimization. Okay. The models can diverge at any time during the training. This requires lots of computation to tune and test. So I wonder if the underlying dynamics that cause this are the same dynamics that result in emergent behavior, which is what they talk about here. They mentioned it up here, but emergent behavior is when you have the model performing at one level and then kind of it reaches this, crosses some boundary, and then it starts performing at a much higher level, almost like a step function. To get rid of pain, TorchScale follows the theoretical derivation of DeepNet to improve training stability. We implement the initialization method of sub-layer norm for Magneto. And then they also implement the deep norm from DeepNet, so some other type of normalization here. And because of this better stability, the models can have larger learning rates. Our mainstream scaling is one mixture of experts. Right, so expert models introduce sparsity to transformers. I don't know what that means. Sparsity to me is a different concept, kind of unrelated from mixture of experts. TorchScale implements XMOE. It leverages the sparsity of a mixture of experts. Top 1, top 2 routing. Gradient clipping. So this is where you, when you're feeding a gradient back through a model, you can clip the magnitude of that gradient so that it's not too big and it doesn't kind of overwrite the weights and biases values that you already have there. They have a novel gradient clipping method, which they call here sparse clip. Okay, so this is what they're going to be doing for their experiments in terms of data. They're using the CC100 corpus, and specifically the English part of that. They're using a pretty old tokenizer here, the GPT-2 tokenizer. So tokenization is taking the raw sentence, right? You you take this sentence, such as the experiments on language modeling, blah, 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 and you turn it into what are called tokens. And tokens, you could think of them like little word fragments, and then also there's a token for a comma, there's a token for the beginning of a sentence, the end of a sentence. So it basically takes a sentence of a bunch of words and it turns it into these little tokens. And those tokens are little vectors, and those are easier to kind of use as input into models because they're all the same, right? Or not, they're not all the same in terms of value, but they're all the same in terms of dimensionality and format. Okay, so they have a big batch size here. Well, it's big for a computer vision world, but not for natural language world. Each sample contains 128 tokens. The models are trained for 50,000 steps on a total of 13 billion tokens. Okay. We start from a Magneto model with 12 decoder layers. You know what? I learned that I can change the color of the highlighter here. I'm going to try to do different colors. So why don't we do 1 is for general highlights, 2 is for, we'll say data set. So let's highlight with this color for the data set, anything that's related to data set. And then we'll do maybe blue for architecture and numbers. So this 12 decoder layers, that's what I would have called depth. And then hidden size, this is what I would have called width, right? So when I was showing you the fully connected layer, that's what I was referring to. Here, I think they're referring to expert. I was going to say this to me is the same exact figure, and they still don't tell you what PPL means. And further scale its depth from 12 layers all the way to 96 layers. Okay, here we go. We evaluate the perplexity, PPL, so this goes here, on the validation set and plot the curves. It shows that TorchScale can successfully scale up the depth. With better training stability, the convergence is smooth regardless of the depth. Okay. And the expressive power grows as the model deepens. So this is validation perplexity. Perplexity machine learning. Okay. So perplexity is the measurement of how well a probability distribution or probability model predicts a sample. So in this case, right, you have in a natural language context, you're usually doing next token prediction. So your model is approximating a function which represents the probability distribution of across tokens for the next word. So it's trying to say, here is the probability distribution of what the next token is going to be given these tokens that you've already given me. And you can, perplexity, right, is a measure of how well that probability model that you have is predicting the actual token that would be there, because you actually know what the next token is because you have some data set. So it's roughly how good your model is at guessing the next token. In addition to the depth, they also scale the width. To scale it up, we replace the feed forward layers with X mixture of expert layers and increase the number of experts all the way to 256. We use top 2 routings as it produces better results in our preliminary experiments. There's a typo here. Let's show it to them. So we can go here. Say save. Typo. We go to their GitHub. We open up an issue. New issue. Typo in paper. Missing space in paper. Smiley face. And let's put in an image. All right, can I copy this and paste? Get some credit. Okay, we use top 2 routing as it produces blah, 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 blah. We evaluate TorchScale on neural machine translation. Okay. Okay, here we have the data set. So 102 languages. Okay, so here are the different data sets they're using. CC matrix, CC aligned, Opus, and Tato EBA. Those are different data sets. They basically combine them, and in total you have 102 languages, 1,932 directions, and 12 billion sentence pairs. Here they're using a different tokenizer, so now they're using a sentence piece tokenizer. And they have a batch size of 262K tokens for 100 steps. Okay, with TorchScale, we implement a Magneto model. The model has 12-layer encoder and 12-layer decoder with 1024 hidden dimension. This is very similar to the one previously. We also evaluate sparse mixture of expert models. Sparse clip. Okay, this is their own novel contribution here that they were saying at the beginning, which is a type of gradient clipping, which is probably implemented in some way that's clever. Standard practice to alleviate the gradient explosion problem. Yeah, so, right. This is what I was saying, where sometimes your gradients get bigger and then they start washing out what you currently have, right? The gradient is ultimately a step, right? It's a step that you're taking in some high dimensional space of your model parameters, and you're taking a little step, and what you're ultimately doing when you're training a neural network is taking a bunch of these little steps, and hopefully you end up in some point in this high dimensional space of all models that solves your problem, right? Or is like useful for solving your problem. So if the gradient is a little step, right, you want those steps to be small so that you're kind of like slowly moving through this landscape, and the kind of mental model that people use is you're a little ball, a little marble rolling on these hills, and you want to get to the bottom of the hill. But if the steps that you're taking, if the steps that this marble takes in this little hilly landscape are very big, you're just going to be like zooming back and forth between the landscape, not really going anywhere, and the likelihood that you end up in like a deep well, right, a local minima, is very low. All right, so this is vanilla gradient clipping here. This is a hyperparameter here, which controls the strength of the clipping. The gradient is G. Then you have L2 norm. Okay, so you take the maximum of the L2 norm of the gradient or this hyperparameter, and then you basically divide the hyperparameter by that and multiply it by G. So if your gradient is much, much bigger, then this hyperparameter, then this number is gonna end up being this here is gonna be less than 1, which means your gradient is gonna be smaller than it is. GD is the gradients of the dense part, and GS is the gradients of the mixture of experts parameters. However, when the MOE gradients become to dominate the gradient norm, making the gradient direction inaccurate after clipping the gradients. We conduct experiments to compare a 256 expert model with its dense counterpart. Figure 3 shows the convergence of the 256 expert model has no significant difference with the dense model. Yeah, so maybe one way to think about why vanilla gradient clipping hurts is if you think about these balls rolling on these landscapes, right? When you have a mixture of experts, you want each of those experts to be a little bit different, right? You want a diversity in your experts. You don't want all your experts to be largely, right? Think of it as you have 10 marbles rolling in this landscape. You ideally want those marbles to be all over, very far away from each other so that they can find different little wells to sit in, right? And hopefully one of those wells is deeper than the other, but at least they're not related. But if you're using gradient clipping, right, all the little balls kind of start from the same place, and they all kind of end up in the same place because they're all taking the same little tiny steps. So, kind of hand-wavy mental model there, but the analogy kind of makes sense in my head. Okay, to deal with this problem, we propose TorchScale, which reweighs the gradients of MOE parameters when computing the gradient norm. Okay, so basically the only thing they're adding here is they're adding this K term here, where K is basically 1 over the square root of the number of experts. So if you have a very large number of experts, you're going to have a very small K. If you have only one expert, right, only one model, K is effectively going to be 1, and this just reduces to vanilla gradient clipping. Figure 3 compares. It shows that sparse clip significantly outperforms, leading to a lower PPL. Okay, so 256 experts, and they're showing you that with sparse clip, you get a lower perplexity, which means your model's performing better than without the sparse clip. Sparse clip has a lower entropy. Sparse clip improves the routing of mixture of experts layers. Gating entropy and training entropy. So this is training steps, right? So here is the very beginning of the model, and then you're training up until here. This is the end of the model, or the end of the training period. So as you're training your model, if you're using the sparse clip, the entropy, you can see it goes down and then it kind of stabilizes, versus without the sparse clip, it stays kind of flat. Number of gradient clippings triggered. Okay, so gradient clipping, right? There's this max here. So you could count the number of times that you have to clip your gradient. And that's what they're showing you here. How many times did you have to clip your gradient? Open source toolkit that enables blah, blah, blah. Wow, damn, I didn't realize this paper was so small. This is actually terrible. Okay, so they introduced TorchScale, open source toolkit that enables scaling transformers. Magneto, DeepNet, improved model generability. Blah blah blah. Yeah, this is no good. I thought this was going to be better, and I apologize. Wow, I thought that given the number of names here and the fact that this comes from a big tech company, I thought that maybe they would put a little bit more effort into the paper, but maybe this is really just all about the software toolkit, and the paper is just kind of an afterthought that was made by one of the kind of interns. Here are the different hyperparameters in the appendices for the models that they use. So this is the number of layers, right? The depth, the hidden size, or the width. This is the I guess the widthiest part of the width, the widest part of the width. This is the number of attention heads. So in a transformer block, you have these attention heads that basically multiply the previous input, the input to that attention head by itself, and you get this kind of like attention matrix. Peak learning rate. So I'm assuming this means the highest learning rate. So usually you have a learning rate schedule, right? Which slowly over time decreases the number of learning rates, or decreases the learning rate. So this is the highest learning rate that you have. This here, Atom, this is a optimizer. So these are the different beta parameters within an Atom optimizer. The Atom optimizer is what determines the magnitude of that little step in the ball rolling on a hill, or the marble rolling on a hill. They have dropout, attention dropout, weight decay, so on. Cool. Maybe let's go to the TorchScale here. Let's actually see. So let's cancel. I wonder if I can. No, I can't. Yeah. Look at their GitHub. So one of the first things I like to do is look at the insights here, and then look at the contributors. Okay, so you can see this repo started November 13th, ends November 27th. Largely, you have Microsoft open source contributing to it, but I think the largest contributor here is this guy here, Shuming Ma, who works at Microsoft Research, of course. You look at commits. Wait for a second for that to load. Little sip of our coffee. So yeah, it's kind of what we're seeing. All the commits happened early on, around the beginning of November. MIT license. Pip install TorchScale. You have your encoder, decoder, of course. I wonder if they have training examples for this. Let's see, examples. Bear seek. Train, here we go. So this is how they trained it. What a terrible train.py. It just imports from Fairseek CLI. All right, let's see. Fairseek CLI. Bear sequence. Okay. So they don't even use their own training. They're using it from here. Facebook research. This is really what they're using here. Where is the train? Fairsec CLI .train. Go back to Fairsec. In here, there should be CLI, Fairsec CLI, and we want train. So this is the actual training. Okay, you got NumPy, you got PyTorch, you got this config object, right? Giant Python dictionary that's probably very, very complicated. You're using OmegaConf. OmegaConf is kind of like a gin-config or one of these Python config manager libraries that allows you to kind of feed in different values to quargs usually. Logger, then you're splitting the data. Okay, there's a quantizer here. Quantizer usually reduces the data type of so your model, right, has a bunch of weights and biases, a bunch of parameters in there, which are a bunch of numbers, right? And these numbers, you can represent them in a very high memory data type or kind of heavy data type, like a float 64, right? Like a 64-bit float or something that's like very, very, takes a lot of memory. Or you can represent them in a very tiny data type, right? Like a uint8, an unsigned 8-bit integer. So these quantizers, a lot of time what they're doing is they're taking a model that's defined with very large and greedy kind of data types and then reducing them to very small data types. Here's your actual train function here. It's the iterator. They have some TPU stuff. Interesting. This is Facebook research and they're using TPUs. Begin epoch. And here you go. Here's the actual iterating. So it iterates over progress. Samples, this is going to be your trainer.trainstep samples. And then here you have the training step for different parts here. Multilingual translation, semi-supervised translation. Let's see what that looks like. You have a forward, backwards steps. Don't have any VIT samples. Open source. This is the group within Microsoft that worked on this. Kind of interesting. They have some Chinese language blogs. Foundation transformers. This is probably the Magneto that they're talking about. Yeah, okay. That makes more sense. So this magneto, oh, wrong. Go. At the beginning here, they kind of shill magneto, Wang al. Wang, it might be the same Wang here. Foundation transformer. Right. There's other types of transformers they could have used, other implementations of transformers that would have been more popular, I guess, or more generic. But they decided to use this magneto, and when I read that, I was like, why would they do that? And then here you go. This is why they did that. It's because they're the ones that wrote the magneto transformer, so they're continuing that work. Cool. So, I mean, we're only 40 minutes in, but we're done. It was kind of a quick one. Yeah, I don't know what else. I think this is good for now. Thank you for listening. Sorry for this being rather short. Next tomorrow, I got a kind of cooler paper for you guys. That's also kind of diffusion models. This was kind of maybe a step to the side to talk about transformers, but yeah, transformers are still king, so it's important to pay respect. And yeah, thanks for listening, and talk to you guys later.